This is section 8.3, day 2, and we have volumes of rotation. And remember this, you must. Anyway, we want to integrate sine squared. And we can't integrate sine squared directly, but we can change it to something that we actually can integrate. And we use the double angle formula. And I've mentioned this once or twice this year already. And we're going to change cosine squared into 1 minus sine squared. So we get 1 minus 2 sine squared minus the 1 over, divide by negative 2. And what we come up with is this right here, where sine squared is 1/2 minus 1/2 cosine of 2x. And we can integrate cosine of 2x. So we're going to change this to, let's see, we can factor a 1/2 out if we want to. So 1/2 integral from 0 to pi over 2 of now that we've factored a 1/2 out of this, it's going to be 1 minus cosine of 2x dx. And then, the integral of 1 is x. The integral of cosine of 2x is sine of 2x times 1/2. Because if you take the derivative, multiply by 2, that's where you're going to get that 1. And then the answer ends up being pi over 4. At this point in the class, I'm going to focus a little less on doing the integral and more just on the setup. I assume you know how to do the integral. All right, anyway, find the volume of the solid by rotating y equals 4 minus x squared. We're going to rotate that around the x-axis, but just from -2 to 2. So let's make a sketch of this. Here's the parabola, -2 to 2. And the parabola looks like that right there. But we're going to rotate this around the x-axis. So here's the 180-degree turn. We're going to rotate that around. Now this graph is right up against the solids, right up against the x-axis. So you can imagine filling this in. This would be a solid circle. So the cross section is a circle. So we're going to integrate the area. And when you integrate the area, you get that third dimension and you're going to get volume. So we're integrating pi r squared, but all these circles are stacking up along the x-axis. So we're going to integrate with respect to x. Well, this variable's r. We want this to be x, but the radius of this circle goes from the x-axis to the curve. So let's pull the pi out. Now we can go from 0 to 2 instead of -2 to 2 and just double this. Because this parabola is symmetric over the y-axis. It's an even function. So we want r squared, but with respect to x. So that's going to be 4 minus x squared squared. So there's the setup. We could FOIL this out, integrate, top minus bottom, and we end up with 512 pi over 15. So take a look at the integral if you're having trouble with it. If you have questions, just let me know, of course. Number 8, we're going to revolve this around the y-axis. And notice that it says x equals instead of y equals, and we're revolving this line around the y-axis. Well, here's roughly the 180-degree turn. And if we rotate this around the y-axis, these circles, here's another one down here, and we can make a much bigger one here. These circles are stacking up along the y-axis. So we're going to integrate with respect to y. Now, it doesn't look very nice, but this is a cone when it's all said and done. So we have a formula for a cone, and it's 1/3 pi r squared h, and the volume is 6 pi, but this is calculus, and we're going to use calculus to find this answer. So the cross sections are still circles, except they're stacking up along the y. So we're going to integrate with respect to y, and we're still integrating pi r squared. We're still integrating the area, and the area is circles. So we're going to factor out pi, integrate from 0 to 2, and now the radius is from the x-axis to the line, which means we need it to say x equals. So that's going to be 3y over 2 squared. And of course, that's going to be 9y squared over 4. We do the integration, plug in the values, and notice we get the exact same answer, except for this, we used calculus to solve that. Find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. So let's make a little sketch of this. X to the third looks like this. Y equals 0 is the x-axis, and x equals 2 is this vertical line. So we're taking this region right here, rotating that around the x-axis. And again, it's right up against the x-axis. So here's the 180-degree turn like that. And we're going to rotate this around. So these are, it's almost like one of those little Sorry pieces if you ever played the game Sorry. So we're integrating circles, pi r squared, but with respect to x because these are now stacking up along the x-axis. So let's factor out pi integral. The radius is from the x-axis up to the curve, which is x to the third. So we're squaring x to the third dx. That's the r squared. Well, that's x to the sixth. We got 1/7 x to the seventh. That's the integral. Plug in 2, and we get 128 pi over 7. In exercises 11 through 20, find the volume of the solid generated by revolving the region bounded by the lines and curves about the x-axis. So we're going over the x-axis. Let's graph this parabola. 1, 2, 3, 4. And it has x-intercepts of 2 and -2. And we're going to go over 1, down 1, over 2, down 4. So we know it's going to pass through these points right here. So it's going to curve something like this. Now, this is a line we want to draw, and it has a y-intercept of 2, and a slope of -1. So down 1 over 1, down 1 over 1. So here's the region that we're looking at right here. Here's the closed region. Now, we're revolving this around the x-axis. So here's the 180-degree turn right there, and it should look something like this. And so we have this washer that we need to take care of. So we have the inside circle, and we have the outside circle like that. So we want big pi r squared minus little circle pi r squared. So let's factor the pi out. We're integrating from -1 to 2. So from -1 here to 2. And we need the big radius. So from the x-axis to the curve, that's the big radius. So that's going to be 4 minus x squared squared, and minus the little radius, the little circle. That's from the x-axis to the line. So we have 2 minus x squared dx. Well, we FOIL out this one. We FOIL out that one. Got the pi. We're going to integrate these. I collected like terms, integrate, and then I kind of gave up on the integral part, and I just grabbed the calculator if you want me to be perfectly honest, and had 108 pi over 5. Let R be the region in the first quadrant closed by the graphs of f of x and g of x as shown in the figure above or off to the right here. Write an equation for the line tangent to the graph of f at x equals 1/2. Well, we have the point 1/2. 1. So we got the point. Now I just need the slope. F prime of x is equal to 24x squared. So f prime of 1/2 is 24 times 1/4, which is 6. So y minus 1 equals 6 times x minus 1/2. So that's not really the chapter we're in. Here's finally the chapter we're in. Letter B, find the area of R. Well, I need to integrate from 0 to 1/2, integrate 0 to 1/2 of the top curve minus the bottom curve. Well, 8x to the third is this curve right here. There's 8x to the third, and the top curve is the sine function. So this is actually the bottom function. That's the bottom. This is the top function. So we need top minus bottom. So g of x minus f of x dx, and we could plug this in and find an answer. Let's kind of skip that for the sake of time. We all know how to use a calculator on this. Let's go to letter C, write but do not evaluate an integral expression for the volume of the solid generated when R is rotated about the horizontal line y equals 1. So here's the horizontal line y equals 1, and we need to take this and rotate around that line. And we end up with this washer. So we have big circle minus little circle. Now we're integrating from 0 to 1/2 because these circles are stacking up. They're vertical. The circles are vertical. They're stacking up along the x-axis from 0 to 1/2. And so now we need big radius. So the big radius goes from the curve, the bottom curve, to this line. So it's not up against the x-axis. It's kind of out here in space. So we're going to take all of this. We're going to go 1. And if we subtract out the function value from the x-axis, if we subtract out this piece, we're left with this right here. So the big radius is 1 minus f of x, and we're going to square that. Oh, I got to factor out a pi here. And then minus the little radius. Well, the little radius is this little piece right here, which if we take 1, all of this from the x-axis, and subtract out the function value, that we're left with this little piece up here, which is going to be 1 minus g of x squared dx.